1D groundwater is chapter 7 in your textbook, and the 2D and the 3D corresponds to chapter 8 in your textbook. And for 2D groundwater issues, in the first lecture, we will be talking about something called flow net method. We do that because we cannot apply Darcy's law directly anymore. For this first lecture, for 2D and 3D groundwater issue, we have two objectives. The first is that you guys need to be able to understand and read something called a flow net. So flow net is two sets of lines, and they form something look like a net. And that net is a tool, it's a graphical tool that we will use to solve 2D groundwater issues. And second is that in addition to the understanding, you also need to be able to use flow nets to calculate the flow rate in 2D groundwater problems. So if I give you a flow net and I give you some other conditions, you should be able to read the flow net, extract some information from it, and use the information that you extract, do some calculation, and get the flow rate. That is the second objective. And to connect this 2D groundwater problem, especially associated flow net, to what we just learned for 1D groundwater problem. First, let's talk about it to move from 1D to 2D and 3D. So for 1D, that's what we learned, and 2D and 3D, that's what we are trying to learn now. And for 1D, we know that is pretty straightforward. We just need to rely on Darcy's law. When we move from 1D to 2D and 3D, the first question is, can we still use Darcy's law to solve 2D or 3D problems? And here I can give out one example. So that's the following figures. So we have one figure here. This figure shows that we have a concrete dam here. And on two sides of the concrete dam, we have different water levels. On the left of it is obvious that we have a water reservoir. On the right of it, the water level is much lower. So because the water levels are different on two sides, let's say that if we have a permeable soil layer below the dam, then we know that water is going to be moving from the left to the right. And this movement is driven by the different in-pressure heads on two sides of the dam. So this is a typical 2D problem, and you will see this a lot in the following lectures. And for this problem, if you try to solve it using Darcy's law, you will also try to get, K, do I have K? Yeah, K is given. What about a delta H and a delta L? Delta H, it seems that it's easy, right? Here, we have one level here, another level here. But what about delta L, the traveling distance? And you will find that it's complicated. For example, you can imagine that if we have a water molecule here, this particle will move from here to here. And if you have another here, it moves from here to here. So you can see that the traveling distances for water at different locations will be different. So it's a 2D problem now. So here, let's just write the answer here. The answer is a clear no. Here, let me offer a little bit more information why we cannot use Darcy's law to solve 2D and 3D groundwater problems. So let's first write down the Darcy's law in terms of Q. We said that we can write that equation in terms of V or Q. And if it's Q, just V times A, and V we know is Ki, and I is the ratio between delta H, that's the head drop or head loss, over delta L, that is the traveling distance of water, times A. For any 2D or 3D problem, as long as we know what type of soil we have, we know K. And for delta H, in many cases, actually, we can figure out what is delta H. We can use this example to explain it. For example, water moves from the left-hand side, so from here to here, and this is the dam. It's concrete, so it's impervious. Water cannot move through it, but water can move through the soil beneath this dam. And the left-hand side, we know that water heads. We have a reservoir here, so we know the total head. On the right-hand side, we also know, because there's a water level here, so we also know the total head. So we know the head drop. In this case, delta H is a constant. But if we take a look at delta L and delta A, we will find that we cannot get a constant value. Because here, if we take a look at different points, for example, point here and a point here, and we will see that they have different flow path. So this is the flow path of the star, and this is the flow path of the circle. They are different. And you can see that the length of the flow path are different for the two material points of water at different locations. So because of that, we don't have a constant delta L. We have different delta L values at different locations. For A, we have the same problem. When we are thinking about the movement of water from the left side to the right-hand side, we want to get a constant A. A is the area of the cross-section. In this case, it's also hard to get a constant A. Because of that, we cannot use Darcy's law directly. For 2D problems, we have the flow net. Before we move to more discussions of flow nets, let me first offer an overview of the whole chapter 8. So that's for 2D and 3D issues. So this is an overview. So I'm trying to give you guys a big picture so you know where we are. So this is the common theoretical basis of groundwater issues. So it's for 1D, 2D, 3D, and you will see what methods are available for different cases. First, you guys need to know that the groundwater movement is described by something called a governing equation. So the governing equation governs the movement of the groundwater. And the name of this equation is called Laplace equation. So please make sure you know this name, Laplace equation. This is required. And for Laplace equation, I can write down the equation for 1D, 2D, and 3D cases. So in 1D case, it is an ordinary differential equation. It's the second derivative of H. H is the water head with respect to the spatial coordinate, that's x, because 1D we only have one spatial coordinate. So second derivative of H with respect to x is 0. And if it's 2D, we know that we have two coordinates. We have x and y. So in that case, we will have this. Second derivative of h with respect to x plus the second derivative of h with respect to y equals 0. And 3D, we just add one more coordinate to it. That is z. We have x, y, and z, 3 directions in 3D. If you guys have ever taken a fancy course such as tensor analysis, you will know that all of these equations, they can be written in the following form. This is not required, so I put this sign here. Just let you know that if you read some papers, you will see this equation. Actually, it's the same thing. But this is the general equation. It will take the form of this for 1D, and the second form for 2D, and the third form for 3D. So it's a general equation. One triangle pointing downward, that means the first derivative. If it's 2, you have a squared there. That means second derivative. For groundwater issues, actually what we are trying to do is that we are just trying to solve this Laplace equation, no matter it's 1D, 2D, or 3D. So we are talking about solving the Laplace equation, and we have different methods. Again, we are trying to offer a big picture for all the groundwater issues, including 1D. The simplest solution is that in a few cases, we can get the solution manually. And that is 1D. So in 1D case, we use Darcy's law directly. And the second type of solution or method is called a graphical method. For graphical methods, we need to draw something or utilize a graph. And that is the flow net method that we will be learning. And the flow net method can be used for any 2D groundwater issues. And it's actually 2D only. And the third type of solution or method is called analytical method. For this one, we have a few special cases in 2D and 3D. In those cases, we have very special geometry and very special boundary conditions. Because of that, people can derive analytical solution, a closed form equation, to calculate the solution to the Laplace equation. So we will also be discussing this one in a later lecture. We are talking about the flow into a well. And the last one is called a numerical method. And this one is actually those computer simulation. Something like finite element, finite difference. And also, we will have one lecture for this one. I will show how to use a very simple graphical user interface-based program to solve a typical groundwater movement issue in 2D. So this one can be used for 1D, 2D, or 3D. Today, we will be doing the graphical method. We will show how to use a flow net to calculate the Q today. And the next, I will show you guys how to draw a flow net. After we talk about the flow net methods and graphical methods, we will also have 2 lectures, one for analytical method, one for numerical method. Let's first talk about the graphical method. That's the flow net method. For the flow net method, there's only one key equation. You can view it as the Darcy's law equation in the flow net method. For that equation, we can calculate the Q using this equation. Q equals K times L times delta H times N sub F over N sub D times B over A. Let me explain the meaning of these different terms. K is the hydraulic conductivity. So we use the capital letter K always for hydraulic conductivity. And L here is not a traveling distance anymore. It's the length perpendicular to the cross section. And we have a cross section for any 2D case. So in this case, in the following example, this is a cross section. And L is actually the length of the structure or the flow field perpendicular to this cross section. So you can view it as the length of the dam. So in the following example is actually just the length of the dam. And there are two key things, NF and ND. NF, the meaning of it is the number of flow tubes. I'll explain what a flow tube looks like. And ND is the number of drops. Some people call it equipotential drops. It's the same thing. And B over A. The meaning of B over A is two dimensions in the flow nets, so I'll show them later. But usually this one equals 1. When we are drawing the flow nets, usually we assume B over A ratio equals 1 to simplify the calculation. Before we move into the introduction to the flow nets, I want to play a video first. In that video, you will see what flow lines look like. And you can get a better understanding of flow net after that.
It's often important to be able to characterize the flow of groundwater. Water in the subsurface can have a major impact on civil structures by causing uplift pressure, seepage, and changing the strength characteristics of soil, among other things. We have fancy computer models that do a good job simulating groundwater flow now, but even today one of the most important tools used by geotechnical engineers is the flow net. Without getting into the nitty-gritty details, a flow net consists of two sets of perpendicular lines which create a curvilinear grid. One set are equipotentials, or lines which connect points with the same pressure. Once the equipotential lines are drawn, the flow lines are just drawn perpendicular to them, forming squares. These kind of simplified drawings make pretty pictures, but do they really reflect how groundwater flows in real life? It's always important to ground truth your calculations, sometimes even with real ground. This model is designed to do just that. It simulates the flow of groundwater around an obstruction to illustrate the morphology and velocity of the flow. It's made of 1/4-inch acrylic sheets cut to size on the table saw. Solvent welding is used to connect the acrylic sheets into a narrow box. All of the plumbing is composed of aquarium bulkhead fittings and clear nylon tubing. Everything was leak tested before the sand was added. Here's how it works. Potassium permanganate is added to 3 spots in the top of the sand. A pump in a bucket below keeps a constant head pressure on one side of the model. The differential between the water level in both sides is what drives the water to flow from one side to the other. Groundwater flowing through the sand creates traces of the flow lines over the course of several hours, illustrating exactly what we estimated earlier with the flow net. The flow of groundwater hasn't always been so well understood. In fact, for some states, regulation of the pumping of groundwater is established on explicit ignorance of its behavior. In a landmark case which cemented the rule of capture into Texas water law in 1904, the court said that groundwater movements are so secret, occult, and concealed that regulating the use of groundwater would be practically impossible. Fortunately, geotechnical engineers since then have developed a foundation of knowledge around the flow of water in the subsurface. It can be a dirty job, but a large part of geotechnical engineering is relegated to abstract calculations and computer models. I was glad to get a chance to take a concept away from the desk and illustrate it with some real dirt and water.
Here, you can see that this glass plate works like that concrete dam, and it separates water on two sides of it. And the water on two sides of it, they have different water levels. And because the difference in the water levels, we will have a pressure head difference. That will drive water to move from one side to the other. And in this condition, water moves from the right hand side to the left hand side. And water always moves from, again, a point with the higher energy to a point with the lower energy. In the demonstration, you see these different purple lines. Actually, they were created because the guy put some dye at different locations on the right-hand side of this glass tank. And if water moves, water will carry the dye as it moves. And that will form that purple lines. Actually, these purple lines, they show the path of the water movement. It's actually one set of line in our flow net. It's called flow line. Let's jump back to our notes. Here, you can see that different water levels on two sides of the concrete dam, and because of that, water is going to move from the left-hand side to the right-hand side. So if we take a look at different points, for example, this point represented by a star, and the point represented by a circle. The water at different locations, these 2 points, they will move through the water underneath the dam to the right-hand side. And actually here, at the toe of the dam, on the right-hand side, we have something called a toe filter. We just put some gravels into it. So what's going to happen is that this is also soil. Water will move in the soil. So when we are talking about flow net water movement, we only consider soil. We don't consider bulk water. So that means water moves from the left-hand side to the right-hand side. And if we take a look at the water at this star point, so we will see that water moves like this. This would be the flow line. And sometimes it's really hard to tell where the flow line is. A straightforward method is just to do that tank test in the demonstration that I just showed. So this red line shows the flow line of the water from this star point. And for this point represented by this circle, water will have another flow line. In this example, how many flow lines do we have? 4, yeah, at least 4, right? Let me mark all the flow lines here using a red color. This is another one, and here's a These are the flow lines. Flow lines shows the path of water movement. Actually, here we are talking about a flow net. We know that a typical net consists of 2 sets of lines, and they are perpendicular to each other. So in this case, we have one set of line, that is the flow line. Actually, another set of line is called equipotential lines. So here I'll use a different color. This is a equipotential line. As I mentioned, these 2 sets of lines need to intersect at right angles. So for any point of interaction, the angle should be 90 degrees. This is required. And in the next lecture, I will show how to draw a flow net. And this is actually one criteria that we need to follow when drawing the flow net. If it's violated, that can clearly tell the flow net is not correctly drawn. So this is equal potential lines. And the meaning of equal potential line is that all the points on that line should have the same total head. So the water head, total water head should be the same on one equal potential line. Same. Here I put if nothing is mentioned, we are talking about total water head. In addition to these two sets of lines, we also need to know a few other things. One concept is called flow tube. Flow tube is the area or the channel or flow channel between two neighboring flow lines. For example, this is a flow tube. So this is flow tube. So between flow lines, we have a flow tube. And what about between equal potential lines? For example, we are moving from this equal potential line and to the next equal potential line. What do we have? We have something called a drop or an equal potential drop. So this is a drop. You can see that we have four concepts associated with a flow net. We have flow line, we have equal potential line, we have flow tube. Some people also call it flow channel. It's the same thing. And we have drop or equal potential drop. And one primary goal of understanding a flow net is to figure out what are flow lines, what are equal potential lines, and how many numbers of flow tubes and how many numbers of flow drops we have here. And here I want to mention a few other things. Here I marked 4 flow lines here, but actually there are more flow lines in this example. That is, if we take a look at here, we know that the dam, the concrete dam, is impervious. So we can imagine that water will flow along the boundary between the concrete dam and the soil, right? Water cannot move through it, right? If water will move along that line, that means that's going to be a flow line, right? So this is also a flow line. Make sure you can understand this. So this is something called a boundary. This is a flow line because water cannot move through it. And at the bottom, here is not mentioned here, but actually this is bedrock. Bedrock, we also believe that it is impervious. If something is impervious, that means water cannot move through it. If water cannot move through it, then water can only move along the boundary between the bottom of the soil layer and the top of the bedrock layer. So that means that boundary will also be a flow line because water can only move along it. So this is also a flow line. I will mark this using a red color. So you can see that we have 2 flow lines on the top and the lower boundary of the soil layer. And let me mark all the equal potential lines. So first, let me mark the equal potential lines inside the soil. Actually, there are two more equipotential lines that we need to know about. One equipotential line is actually the line here. That's the bottom of the reservoir, or the top of the soil layer on the left-hand side of the dam. The reason is that, based on what we learned in the previous lecture, you guys can figure out the total head at different points on here, on this line. They should have the same total water head. So if you cannot understand this, so please come to talk to me. That's what we discussed in previous lecture. You can try to get the total head at different points on this blue line. So you can get the pressure head. You can get the elevation head is from here to the datum, depending on where you set the datum. And you will see that the total head will be the same at every point on this line. And it's outside of the soil, so we can get the pressure head directly by taking a look at the height of the water column above it. On the right-hand side, we have the same thing. So we have another equipotential line here, because every point on this line, they should have the same water head. Actually, this one will also be the same. This is also the equipotential line because it's connected to this line. And we use very coarse gravel, so the pores are pretty big. We assume that it will not consume water head for water moving through this material. So that's why we assume they have the same potential. There's no head loss. Now we draw all the flow lines and equipotential lines. The next task, we need to figure out how to count the number of flow tubes and the number of equipotential drops. So could you guys try it yourself to see what you will get for N sub F and N sub D in this case? N sub F and N sub D. Could you guys try it yourself? Just count it. So again, N sub F is the number of flow tubes, and a flow tube is the channel or the area between any two flow lines. So how many flow tubes do we have in this case? How many? 5. So let's see. Oh, let me move this up a little bit. Let's do it from the top downward. So we have the first one here, right? Then second, 3, 4, 5, right? So we're talking about flow tubes. Flow tubes, we have this is the first one, second one, third one, then fourth one, and the fifth one. So we have 5 flow tubes. And how many drops do we have? 9. How many? Let's do it from the left-hand side, following the direction of water movement. So from the first blue line to the second one, we've got the first one, second, third, fourth, fifth, sixth, seventh, eighth, ninth, right? 9 of them. Let me use a blue color to represent the number. So let's do from the left to the right. 1. Let's do it here. 1, 2. So this is the first one, drop. Second one, 3, 4, 5, 6, 7, 8, 9. So there's 9 equipotential drops. As I mentioned, as long as you know how to count NF and ND and know how to use this equation, you know how to use the flow net. And again, for B over A, to simplify the calculation, we always assume that the ratio is 1. So you can just overlook this ratio when you do the calculation. Let's work on one example together. Try to get a better understanding of how to use this method for solving problems. For this problem, we are still working on the flow net shown previously. So that's the flow net that we just worked on. And for that one, we know F, that's the length of the dam, or the length normal to the flow net. So that is 2 kilometers. And we know K, that's the hydraulic conductivity. That is 1 times 10 to the power of minus 5 meter per second. And we know H1, 55 meters, H2, 10 meters, and H3, 100 meters. I will mark these different H values. Let's see what are required. First, we need to identify NF and ND. That's actually what we just did. Second, if we set the datum at the top of the bedrock, that's also the bottom of the soil layer. Please calculate the total water head at point A, B, and C. I will mark location of A, B, and C. The third part, we need to calculate the flow rate based on the information that we can collect from the flow net. Let's jump back to the figure and you see where are A, B, C, what are the H1, H2, and H3. In this case, H1 is here, so it's already marked out. H1 is 55, and the unit is meter. And H2 is 10 meters. And H3 is this one. It's distance from here to here. This is H3. So H3 is 100 meters. So this is also H3. It's the same. Oh, sorry. It goes to the top of the bedrock. And we also need to mark the location of 3 points A, B, and C. This is point A. That's the point where this star is located. So this is point A. And the point B is here. So this is point B. Point C is here. So A, B, and C. Make sure you mark the correct location of A, B, and C. Let's get back to the problem. So solution. First, we need to calculate NF and ND. And we've already done that. So NF in that flow net is 5. And ND is 9. Second, we need to calculate the total water head at a point A, B, and C. For the total water heads, in the previous chapter, in order to calculate the total water head for any point inside a soil, the procedure that we did is that first we calculated something called the hydraulic gradient, right? That is the gallon per mile. And then we try to see the distance of the water traveling. So that's how many miles that we will do. So we times the gallon per mile, the hydraulic gradient, and the traveling distance. So we can get the head loss from one point to another. From one point outside the soil to one point inside the soil. Here, actually, we do it in a similar way. But now it's different. We don't calculate the I directly. We calculate the head loss per unit drop. So it's like we don't do it in a continuous way. Now, everything is discrete because we are talking about a net. We are talking about lines. To do that, first, let's calculate the total head loss. The total head loss in this case is delta H equals H. If we get back to the previous figure to see the head loss. So the head loss is the difference between the total head at this line, the first equipotential line, and the line on the right. You can see that the total head at the first equipotential line is the pressure head 55 meters plus this 100 meters. So it's H1 plus H3. And the total head on the right-hand side, that's the last equipotential line. It's H2, 10 meters. That's the pressure head, plus the H3. So that's the elevation head, because the datum is here. Get back to this. So this one is H1 plus H3 minus H2 plus H3. And we will get 155 minus 110. We will get 45 meters. So that's the total head loss when water moves from the first equipotential line. That's the starting point of water movement to the destination of water movement. And here, because we don't have a constant water traveling distance, so here for delta H, there are ND equals 9 equipotential drops. So that means for one drop, we will have delta H1 equals the total head loss over the number of drops. So we have 45 meters and we have 9 drops. So we know that we're going to have a head loss about 5 meters per one drop. That's something that's similar to the I, similar to this one. So I just put it here. That's the hydraulic gradient. It's actually very similar. Here we use a different symbol for it because now we are not talking about traveling distance. As I mentioned, water molecules at different locations, they move along different water paths. So the traveling distance will be different. There's no way we can compare that. So in order to take care of that, now we are talking about the drops instead of traveling distance. So we are talking about how many drops you travel. So based on the number of drops, and the I is the head loss occurring over one head drop, we can calculate the head loss from one point to another point inside the soil. So we got a delta H1. We put 1, that means one drop. So the meaning of 1 here is one drop. So you can see that now a head loss of 5 meters will occur over one drop. We already got NF and D. Now we are doing second part. We need to calculate the total head at A, B, and C. So at point A is connected to bulk water. So that means we can read the pressure head directly. So the pressure head is the height of water column above it. So here, this is HPA. And here you can see this is 55 meters. And the elevation head is obtained based on the datum. Here we set the datum here at the top of the bedrock or the bottom of the soil layer. So it's the distance from here to here. And in this case, it's H3. And H3 here is 100 meters. So the total head of point A is 55 meters plus this is 100 meters. So H1 plus H3. That's point A. So HA equals HPA plus HZA. And HPA here is H1, plus H3. So here is 55 meter plus 100 meter. We got 155 meters. And then we need to calculate the pressure head of point B. To do that, let's take a look at a flow net again. Point B and point A, they are on exactly the same flow line. That means we can imagine that the water will flow from point A to point B. And here from point A to point B is here. How many drops we have? From A to B. How many? 2. One drop is just the distance between two neighboring lines. 1, right? So just from this line, the first blue line to the second blue line. So there's only one drop. So one drop, we'll get it back to this. From A to B, there's only one drop. So that means HB, the total head at point B, will be HA minus the head loss. And the head loss is one drop times delta H, delta H1. So that is the head loss per one drop. So in this case, it's 150 meter minus one drop times 5 meter per drop. So we will get 150 meter. That's HB. For HC, we do it in the same way. Let's take a look from A to C. What happens? From A to C, we can see that first. They are not on the same flow line. So that means water does not flow from A to C. But we can imagine there's another point here. If there's a point here, D, water should flow from point D to point C. And both point D and point A, they are in contact with the same bulk water. So they should have the same total head. And actually, you can do the calculation. It's the same. The water column above it and distance from this point D to the datum, that's the bottom of the solid layer, the total should be the same. So the total head is also 155, the same as point A. From point D to point C, how many drops do we have here? Point D to point C, 3. First one from here to here, right? 1, 2, 3. So 1, 2, 3. 3 drops. Get it back to here. So when we analyze from point A to C, we find that it should move from point D. We add a point D here. Not from point A to C directly, but point A and point D, they have the same total head. And we have 3 drops. Then point C equals HA, or is the same as HD, minus 3 drops times delta H1. So we will get 155 minus 3 drops times the same 5 meter per drop. So we will get 155 minus 15, and we get 140 meters. That is the total head. We know the total head, and if we can get the exact location of B and C, actually we can also get the elevation head. With the total head and the elevation head, we can also calculate the pressure head and the B and the C. This is part 1. Part 2, and for part 3. For part 3, we need to calculate the flow rate. That's how much water that we can collect on the right-hand side of the dam. For this one, we just use that equation. Q equals K. In the past, we said that the Darcy's law tells QIA, but now we use the graphical method. So now it's a little bit different. It's K L delta H times NF over ND. And there's also a B over A here, but we said that when we are drawing the flow net, we want to make sure this ratio equals 1, so we don't need to consider this one. You don't need to remember these equations, don't worry about it, but you need to know the meaning of each term in this equation. I need to know how to get each of them by reading a flow net. We plug in all the values that we have. K is 1 times 10 to the power of minus 5 meter per second times L. That's the distance. I think it's given here is 2 kilometers here. So let's use the same unit. 2 kilometers is 2,000 meters. And then times the delta H. We got it. In the first step, it's 45 meters. And then NF and ND, we got it in the first step. NF is 5 and ND is 9. And here B over A is 1. So we do the calculation, we will get 0.5. You want to take a look in what volume that you will have. Actually, before you do the calculation, you know that flow rate should be cubic meter per second. So here we double check. Here we have a meter per second, meter and a meter. So we will get a cubic meter per second. So at least the unit is okay. In this case, we did not miss anything. So this is how to use a flow net to solve problems. You can see that we are still trying to figure out basically two things. One thing is the water head at any point inside the solid layer. We need to know how to do that. Second is how to calculate the flow rate or the velocity. And for 2D case, we cannot get a velocity, but we can get the flow rate. If you want to build a dam to hold water behind the dam as a reservoir, sometimes you need to calculate how much water you can expect to receive on the other side of the dam. And this is the application. So based on what we learned, now you are given a flow net, you should be able to calculate the flow rate. And also you can calculate the water head at any point in the soil beneath the dam. We have a few applications. For example, sometimes we need to calculate the uplift pressure. Sometimes we need to calculate something like erosion, piping stuff. That's also needed. With this in mind, if we can go to here, you want to calculate total head at point B. We just need to see how many head drops we have from point A to point B. And here you can see that there's only one drop. So that means the total head at point B will be 5 meters lower than the total head at point A.
I think I'm falling for you.